All right, so today we are going to be covering growth and decay functions. So let's go and get started. So the first thing that we're going to do for this warm-up is we're going to determine the constant ratio for each sequence. So the constant ratio is pretty much trying to determine 5 times what is going to give us 5.25. 5.25 times what is going to give us 5.5125. And so how we are going to go about doing that is pretty much just solving for x using that first equation. So you're going to take your second term, which is that 5.25 divided by 5. And hopefully you get 1.05. And that is your constant ratio for this first sequence. All right, so let's look at number 2. Oh, I forgot to say what page this is on. If you have your textbook, this is on page M3, 107. If you do not have your textbook, just like last time, just take these notes by hand. And if you need to pause the video and take your notes and then click play again. So the second one, what you're going to do this time is exactly the same thing. You're going to take that second term divided by your first term. And hopefully for this one, you get 1/5. Would be the constant ratio here. So finally, number 3, this time you're going to have 2/3 divided by 1, and that will end up giving you 2/3. Anything divided by 1 is going to be that number. All right, so now we are going to be wakey, eggs and bakey. So we have studied linear and exponential functions at this point. You know the linear function increases or decreases by a constant difference, whereas an exponential function increases by a common ratio. So that common ratio is exactly what we were just finding up here, except it was a constant ratio, but it's constantly going to be multiplied by 2/3 to get your next number, and that makes it a common ratio. So we are going to now look at some functions, and they're all shown right here. Some of these you can look at them and determine that they're linear functions, and some of which are exponential functions. Here on this next slide, we are going to write each of these down. So I'm going to zoom in a little bit over. Actually, I think we're going to click back and forth, probably be our best option. So let's look at f of x first. Hopefully you recognize that f of x is going to be a linear function. I think we're just going to write linear on all these. So linear or exponential. So the reason that's linear is because you have -3 times x minus 1. The x is not in a power. So for example, g of x, you're looking at 2 to the x plus 5. So because the x is up here in the exponent area is what makes this an exponential function. All right, h of x, again, exponential. Q of x is exponential. R of x, exponential. So over here, we do have an exponent in this problem. It's 2 to the 3rd. But because it's a number there, not our x, this one will be linear. Write that one in purple. Back down here at a of x, we're back to exponential because that x is in our exponent spot. This next one is linear. Again, the x is in the problem with all the numbers. It's not in an exponent. And then finally, this last one, again, is an exponential because of the placement of that x. So if you're writing this in your textbook, you can just write underneath linear f of x, b of x, and t of x. And under exponential, you can write g of x, h of x, q of x, r of x, a of x, and c of x. So if you wanted to list all these here, which I will now, linear, what's that? F of x, t of x, b of x, g of x, h of x, q of x, a of x, r of x, and c of x. All right, so now let's go ahead and look at number 2. So we're now going to sort the functions into increasing and decreasing functions. Whenever we're looking at those linear functions, which, let's see if I can make this picture over here a little bit bigger. And we'll just do increasing first. So y'all know with linear lines, your slope, if your slope on a linear line, so let's write linear, slope is positive, it is an increasing function. Slope is negative, it's a decreasing function. So let's look at f of x first. Is that going to be an increasing or a decreasing function? Which actually, I'm just going to make this extra big and we're just going to write it underneath the picture. But on y'all's work, you can list them under the increasing and decreasing. But if we're looking at negative 3x, so our slope here is negative 3, so that is going to make this a decreasing function. Our other linear function was t of x, which is down here. Again, negative x, so again, this one will be decreasing. And then down here, b of x was our other linear function. Whenever you distribute this 5 in, you'll have positive 5x, so this will be an increasing function. All right? So for exponentials, I guess we'll write this right here. Your b value, if your b value, so we're looking at 0 is, our b is between 1 and 0, it is a decreasing function. And if b is greater than 1, it is an increasing function. All right, and so that b value comes from the exponential equation. And so an exponential equation is y equals a times b, which we should probably put a dot instead of a, looks like an x. So a times b to the x power, which I probably should have gone over that earlier whenever we were talking about these. But these are all a times b to an x power. A times b here is 0.5 to the x power. So all of those kind of things. So we were determining this off our b, which is the number that our exponent is on, okay? So, for example, g of x, we're looking at positive 2. Positive 2 is greater than 1, so this is going to be an increasing function. Which let's do all increasings in red this time. So, whenever we're looking at h of x, that's 0.5. 0.5 is between 0 and 1, so this one is a decreasing function. If we come down here and look at q of x, again, we're looking at that b value. And down here, our b value is 1.5, which is greater than 1. So q of x is a increasing function. Whenever we come and look at r of x, this would be an example of where the negative in front of the a value is kind of what matters here. Because if we were to simplify this out, you'd be looking at negative 9 to the x, which would give us a negative b value. And that is the reason that this one is decreasing. Whenever it's something that's kind of confusing that you may not know, I would recommend coming to your calculator. Let's graph this one real fast. So if you can't look at it and it's obvious of which one would be, because this negative 3 times 3 to the x is a little confusing. So let's plug it into the calculator and look. To that x power, and let's click zoom 6. So see how our graph, we're going straight and then we're kind of decreasing. So that is where we get the decreasing from here. Because what that is showing us is whenever our original 3, our a value, is our starting value of this function. So we are starting at negative 3, but because we're starting at negative 3, we are going down with this function because it's negative 3 times 3 to the x. And that one's a little confusing, so if you're struggling with that one, it's okay. That's probably the hardest one on this whole page. All right, so now let's look at a of x, and that is 10 times 1 to the x. And because we are at 1, and whenever we're looking at our b values, b1 is never included. So this one is actually neither. And let me explain that here in a second. So the reason for that is because we're starting at 10, and our constant ratio here is 1. So we're constantly going up by 1. So that is what's making it a constant ratio. And if you look up here, our constant difference as well. It's making it a constant difference between the numbers because it's 1. So that is why that one is actually neither. Again, R of x and A of x are definitely two of the harder ones to understand on this page, but typically you will not see ones that difficult. All right, so let's look at C of x. So we're looking at 1 minus 0.1. So that is end up going to be less than 1, but it's obviously going to be greater than 0. So that one is also a decreasing function. All right. All right, so now we're at activity 2.1, calculating interest with linear and exponential functions. So let's consider which function type represents each situation. I believe it's Sonia is what we're going to call her. I may be saying that name wrong, but her family deposits $20,000 in an interest-bearing account for his college fund. Sonia account earns simple interest each year. They put some really crazy names in here. So, Chiconde's family deposits $20,000 in an interest-bearing account for her college fund that earns compound interest each year. So the difference in these two is one of them earns simple interest and one of them earns compound interest each year. So, and then the next thing on your page is showing a table of the simple interest balance and the compound interest balance. So you can kind of recognize here that this one is going up by $800 a month. You can really tell it between the first two. The other ones you have to do a little bit of math to figure it out, or the first three. So because of that, we know that this first one is a common difference. The compound interest balance, you can tell that the first time it goes up by $800, but then it goes up by $832. So this one is not increasing by the exact same thing every time. So that is why that we know this one has a common ratio. All right, so we're going to look at 1B. In the textbook, there's a sketching of the graph. This graph is so hard to tell that one is an exponential and one is a line whenever you go in and graph these. So we're not going to worry about the graphs of these functions. We're just kind of going to look at them and observe them and gather some information. So we're going to write a function s of t to represent the simple interest. I'm going to make this picture a little bit bigger so we can see it better. So we're going to write a function that represents that simple interest account. So this one does end up being a linear line. So hopefully you'll remember that whenever you are writing a linear equation, you need to know your y-intercept, which is your b value, and your slope. Your slope is the rate at which you are increasing with this, the common difference. And the common difference here is that 800 that is being added each month. And our zero is that $20,000. Okay? So with the compounding interest one, this one is an exponential graph. So as we talked about earlier, we start with our A value. Our A value is our starting value here. So the starting amount in this account here is, again, that $20,000. And then we got to do a little bit of math to figure out what our common ratio is here. So we're going to do the exact same thing that we did last time. We're going to take our second value divided by that first value. And hopefully you get Double checking my work here real fast. I got 1.04. So this is times 1.04 to the x power. All right. So now we're going to use these functions to determine each value. So we did label S of t, that's that linear one, and C of t, that compound interest. So S of t, we're wanting to figure out when it's 5. The t is equal to 5 here, so we're just going to plug in 5 to our equation. So you're looking at that $20,000 plus 800 times 5. All right, so we're going to go and plug this in our calculator, which if you are in the textbook, it says A on this PowerPoint, but S of 5 is actually D in your notes. So what you're going to want to do is come to your calculator, 20123 plus 800 times 5, and you get $24,000. For B, we're looking at C of 5. So you're looking at times 1.04 to the 5th power. In y'all's textbook, this is C. So I don't know why they got these out of order on this PowerPoint versus the book, but I didn't check earlier. I'm sorry, my bad. But this is C in your book. So whenever you plug this into your calculator, what you're going to want to click is 1, 2, 3. Is that right? Yeah. Times 1.04 to the 5th power. Definitely round to the second decimal place because we're talking about dollars here. So this will end with 6 cents. But it was $24,333.06. All right, I'm going to have y'all do, this is actually B out of the textbook, but it's C on my notes. Again, sorry about that. Actually, this one's not in your book at all. In your book is C to the 6th. So let's do C to the 6th, actually. So I'm going to write the equation up here, just in case you aren't looking at it right now. So this is that $20,000 times 1.04 to the 6th power. Y'all go ahead and type in your answer and put it right here, and then I'm going to have to go and figure mine out. All right, so I'm going to just double click up so I don't have to type it all out again. Over 6. 25,306.38 cents. So that would be your answer there for y'all's B. I don't know why they got these numbers all mixed up. Again, they did it wrong here. So this is actually supposed to be your A, and it's not a 4, it's a 6. So this was the linear one again. So plus 800 times 6. I have to type it in my calculator too, so let's do it together. Actually, I'm just going to click up and click over 6. $24,800. All right, so pretty much with these, you're just plugging in those values to figure out how much money you would have after 6 years, I believe is what we were looking at. Yes, 6 years. Our time was in years. All right, so now we're going to determine the average rate of change between each pair of values given for each relationship. So the simple interest here, because the rate of change each time we were going up by $800, you really just can, I'm okay with y'all just inferring that because you're looking at a line. It's going to go up by $800 each time. But for our compounding interest, because we're going up by our common ratio, we are going to have to determine the slope between those points, we're going to have to do y2 minus y1 divided by x2 minus x1, which I am going to probably move this table, and those values are not going to go with it, but I will erase them and rewrite them here in a second, I promise. We just need some room to work out some math. So this was 800, 800, because again, we were talking about that line, so we know the slope between those points. X is t here, so for this first equation, you are looking at 1 minus 0, and your y2 and y1 are actually on your original table, so if you look back, it's that original $20,000. Oh, sorry, that would be y1. That's your 0. You start with 28. Sorry, 20,800 minus 20,000. And for here, when you plug this in the calculator, hopefully you got 800. All right, for 1 and 2, again, you're going to have 2 minus 1 on the bottom. 2 is also given to y'all at the very, very beginning here, and it was 21,632. I do believe one was also given to you. It's that $20,800. When you plug that in, you should get 832. And again, if you don't know where I'm getting these values from, it's all the way from this original table. Because see, we're given 0, 1, 2, and 3. So I got 0, 1, and 1 and 2 from that original table of values. So you can flip back and look at those. 6, though, we are not given. So we are going to have to calculate for what 6 is, which I believe we have already done. So it was that C of 6, which is right here, that $25,306.38. We did not calculate it for 10, though, so we will have, we're given 10, aren't we? Yes, we're given 10, so we don't have to calculate 10, but we did have to calculate that 6. So we already got that 6. I'm going to write that point over here just so that we don't forget. 25,306.38. All right, so we'll have 6 minus 2 all over, and that 6 was that 25,306.38 minus that 2, which was that 21,632, which barely fits on here perfectly. Whenever you type that in the calculator, hopefully you got 918.60. And then finally, our last one, you're looking at 10 minus 6. The value that was with 10 was 2,9,604.89 minus 35. Not 35, sorry, 25. I cannot read today. 2,5,306 and 39.38 cents. And hopefully you got 1,704.63. All right, so let's go and look at number 4 here. And we did get all of those values correct. So compare the average rate of change for the simple and compound interest accounts. What does this tell you about the linear and exponential functions? And hopefully you remember the simple interest is linear, and this is the exponential. So our average rate of change for the linear, it's constant. As our t-value goes up, our average rate of change is staying the same, so it's constant. Our average rate of change for the exponential, it increases as x increases. So if you put your money into a simple interest function, you're going to be making less money in the end than in a compound interest function. All right? All right, I think we're going to skip a page in here because there was a number 5 and a number 6 that we're going to skip over. And we're going to go ahead and get to 2.2. Analyzing exponential growth and decay functions. So in 2018, the population of Chicago, Illinois was about 2.7 million, and the population of Columbus, Ohio was 880,000. Chicago's population has decreased from 2010 at a rate of 0.4% each year. At the same time, Columbus' population has grown at a rate, so it's growing at a rate of 0.14 each year. So which city's population can be represented by the increasing and which can be represented by the decreasing functions? So the increasing one is obviously the one that's growing. So that would be Columbus. We'll start with that one. Is increasing. And our Chicago population was decreasing. All right. So let's examine the properties of the graphs of the functions for Chicago and Columbus. And I went ahead and put the function equations up here, where these numbers are coming from again, because remember this 27 million, that was the initial population. And then we have 1 minus that percent that we were decreasing by to the t power. And then for Columbus, our original population was at 880,000, and we are increasing, so we have 1 plus the decimal of that percent for every year to the t power. So as you can see, g of t is Chicago, and it almost looks like a linear function. It's not, though. It is very slightly decreasing because that percentage is so small is why it looks almost linear. But because our percentage is a little bit bigger over here with b to the t Columbus, you can see how it's increasing more. So these are both exponentials. This line does look straight, but I promise you it's not. It's a little bit curved, okay? So now we're going to answer some questions. So the a value, so hopefully y'all remember from earlier whenever we wrote that f of x equals a times b to the x. So that a value is what we are starting with here. So as you can see, for Chicago, we started with that 2.7 million, and that is what is shown there. So the a value represents the original population. So, but our a values earlier, let's come all the way back up here. Where's our equations? Right here. So our a values earlier, remember, is where we were starting with that dollar amount. So your a value is pretty much whatever function you're looking at. It's where your starting value. Earlier we were talking about money. Now we're talking about populations. All right, and our b value represents the rate of increase or decrease of our population. So rate of increase or decrease of population. Ooh, it's barely going to fit. All right, we're going to skip C and number 4, and we're going to read down here at the bottom. So consider an exponential function of the form f of x equals a times b to the x when a is greater than 0. An exponential growth function has a b value greater than 1, and it is of the form y equals a times 1 plus r to the x, where r is the rate of growth. So because we were talking about population, it's growing at a certain rate. The b value is 1 plus r. An exponential decay function has a b value greater than 0 and less than 1, and is of the form y equals a times 1 minus r to the x power, where x is the rate of decay. And the b value is our 1 minus r. All right, so the last thing that we're going to look at is this activity 2.3. We're going to be comparing increasing and decreasing exponential functions. Consider 6 different population scenarios. So they're going to give us a scenario, and we're going to determine which function it is. how I like to go about these, I like to just write the function and then go and look at these and determine which one it is. So we can cross them off of our list. So Aliso, I do not know how to pronounce this, but this place has a population of 17,000 people. So remember, that's our starting value. So that's our A. Times its population is increasing at a rate of 1.5%. So it's giving us the percent value here at which we are increasing. So remember, that'll be that 1 plus, and remember, if we're looking at a percentage, and we're going to need a decimal for this problem, if we're looking at 1.5, we've got to move our decimal to the left twice. So this will be 0.015 to the x power. So that'll be that first function there that we're crossing off. Oh, wait, no. Sorry, the second. That first one has a minus. All right. So let's look at Charleston. Has a population of, again, we're starting with that 17,000. Its population is decreasing at a rate of 2.5%. So let's get that into a decimal. So 1, 2. And that's 1 minus 0.025 to the x power. Now, if you look over there at that table, they're wanting us to determine what our actual b value is here. They gave us our rate, which is that r value, but we need to find our b value. So if you type in your calculator 1 minus 0.025, hopefully you get 0.975 to the x. Now let's check and see if that matches any of our answer choices. We already got rid of this one and this one. Oh, it is that one. That's why we're getting rid of it. All right, so let's go ahead and look at Youngstown. I'm going to let you all go ahead and write this for Youngstown. Just remember, you're given your rate here, and we are decreasing. And we know that we are not going to be that plus or that 0.975. All right, so hopefully y'all recognize we're starting with 17,000, and we are decreasing by 1 minus 0.015, because we're starting here and moving to the left. All right, let's see if that matches our one left. It does. So we have gotten rid of the top 3. All right, so let's come down here. Now we're talking about Point Park, has its population of 17,000. It is increasing by 2.5. Let's move that to the left. Minus, it's increasing, so we're going to add 0.025. We're going to have to figure out what it is. Hopefully you can look over there and recognize that this is going to be 17,000 times 1.025 to the x. Do not forget your exponent up to the x. That's very, very easy to forget. So we have now gotten rid of all of those, and we have 2 left. Okay, our rate is 10% here. 1, 2, so we'll be at 0.1. So starting is still the same. We are at 1. Are we increasing or decreasing? We are increasing 0.1 to the x. So this will be 1.1 to the x power. Bring that 17,000 down. And that will be this last one. So we're going to have 1 left. So our final one, we're increasing at a rate. So that'll be 17,000 times 1.01 to the x power. It was also our only option left. So they each have a match here, and we are good to go. So yes, that's the end of the PowerPoint. So these are the notes for Friday for A Day, Monday for B Day. Your homework tonight is going to be the review for your quiz that you will have on Tuesday for A Day and Wednesday for B Day. It's a 10-question quiz. I'm giving you, actually I think it's a 9-question because I don't even think it's 10 questions. I'm even making it a little bit easier on y'all. I'll give you a point just for putting your name on the thing or completing it, which way you want to call it. So this is actually A Day right here. So M3 T2 exponential review. And as soon as this pulls up, I'll show you. All right. So rewriting exponential below the rational exponent, write it in radical form, simplify the expression. That was all from exponential functions and rational expressions notes the other day. Number 4, 5, 6 are all from notes from today. You're just looking at those functions and determining what it is. Which of the expressions equal 4? Plug them in your calculator, figure out which one equals 4. Which function will have a greater output of x equals 10? You're going to have to make equations for these to figure that out. And then number 9 is also the notes from today. So go ahead and start working on this. I am going to go ahead and post the review, or me going over this review with you. So whenever you finish it, you can go ahead and watch that video. If we are back in school, actually, we are planning at this moment of me recording this video, we are planning on being back in school next week. So I will go over the review with you in class if you're in person that day. And if you're a distance learner, the review will be up as a play pause it as well. So go ahead and watch that video and take that quiz. On that Tuesday and Wednesday, once you have finished your quiz, you need to go into Skyward. You need to check your grades to see if you have anything missing. I will be posting this document. This has all of the grades that are in there for quarter 2, even the quiz that you are taking on the December 15th and 16th. Guys, if you are missing something on this list, you need to read whatever's in red above it to figure out where you need to get this assignment. Homework assignments, they need to be submitted into Seesaw. You need to go to this date on the plan book. If you can't find it, you need to click this link and watch that video. Quizzes, you need to email me so I can unlock them for you. And then you can go and click on the original link, which is on these days, to take that quiz. Test. If you are missing a test for me, you have to contact me and I will email you a link to take it. I'm not opening up the old test links, okay? Math yet. There's 2 grades for each of these. So this is 6 grades right here. You need to have module 3 finished. So if y'all have any questions, you can join either the Zoom call that's the last 15 minutes of class, or message me on Remind or on my email. If y'all have any other questions, please let me know. The end of the semester is almost here. The last 2 days of school will be for makeup work. So I would not rely completely on those 2 days if you're missing a lot of assignments, though. We got to get these assignments turned in and get to passing, okay?